Hello, welcome everyone, and thank you for joining us for this episode of Spectroscopy in Action, our live webinar series. My name is Maria Tessa, and I'm the product manager for photoluminescence at Edinburgh Instruments. Joining me today is our application scientist, Tommy Lone. Tommy and I are going to deliver today's webinar on measuring scintillation or how to optimize radioluminescent materials. In this webinar, we are going to give you an introduction to scintillators and their practical applications, and we will discuss how to characterize the radioluminescence from spectral to advanced time-resolved measurements. At the end, we're going to have a Q&A session, so you will get the chance to ask any questions you might have. I hope you all enjoyed this webinar, and I will now pass over to Tommy to get started.
Thanks, Maria. So today in this presentation, it's going to be split into two parts. The first half, I'm going to go over a bit of the background to this topic. I'm going to talk about what radioluminescence is and what are scintillators, the different types of scintillators and what they can be used for. I'll also go to bit into the theory of mechanism of scintillation and how we can use radioluminescence spectroscopy to optimize their properties. I'll then hand over to Maria, and she'll talk about how we can measure radioluminescence practically with our XS1 radioluminescence chamber, and also talk about some case studies from literature where researchers have used the XS1 to optimize the properties of their scintillators. So first of all, what is radioluminescence? So radioluminescence is the emittance of UV or visible light, or less commonly near-infrared light from a substance when it's been excited with high-energy ionizing radiation. So this is things like X-rays, gamma rays, as well as high-energy particles such as alpha particles and beta particles. And we use the term scintillators to describe substances that exhibit radioluminescence. It can be solids, liquids, and gases. And the term radioluminescence is used to describe the processes of scintillation and also Cherenkov radiation, which I'll explain a bit more about later on. So there are many different types of scintillators, all liquids, solids, and gases. We'll talk about three main classes of them here. So the first one is inorganic crystals. So this is things like bismuth germanate, thallium-doped cesium iodide or sodium iodide. There are also organic materials such as crystalline anthracene, and such as paraterphenyl and diphenyloxazole, which can be act as scintillators in solution or as in plastics for easier handling. There's also another class which is becoming increasingly important, is becoming the next generation of scintillator detectors, which are nanomaterials. So this includes things such as perovskites and quantum dots, such as like cadmium selenide and lead sulfides. So things with quite high molecular weights to absorb X-rays. So scintillators are ostensibly used to detect ionizing radiation and high energy particles by converting it into UV or visible light, which is more easily quantified using a camera or a photomultiplier tube. So these are used in medical imaging, so taking X-ray scans for CT, and also for measuring radio tracers in positron emission tomography and single photon emission computed tomography. They're also used in baggage scanners to detect dangerous weapons in airports, and they're also used quite a lot in high energy and particle physics, so for detecting high energy particles, cosmic rays, and these are used in the Large Hadron Collider at CERN. So this is a bit of a summary of different types of scintillators and what some of their properties are. So one important aspect of a scintillator is its light output. So it's how efficient is it at generating optical light from ionizing radiation. Another property is the decay time. So how fast is the scintillator able to convert the ionizing radiation into UV or visible radiation? And this will determine what kind of applications are used for. So we can kind of see broadly that inorganic crystals will have quite a large light output, but will have quite long materials will have a lower light output, but are able to resolve faster events. So these are what used for fast neutron detectors and high energy physics, whereas inorganic crystals can be in baggage scanners or environmental radioactivity detectors, which don't have to be detect so quickly. So what is the mechanism of scintillation? Well, it depends on the different type of material it is, whether it's an inorganic crystal or an organic material or a gas. But here we're just going to talk about inorganic crystals, so things like BGO. Um, and for these type of materials, scintillation takes place over three different stages. So the first one is conversion. So this is the interaction of the ionizing radiation with the scintillator to generate charge carriers. So this is electrons and positive holes. The next stage is energy transfer. So this is the migration of these charge carriers through through the scintillator until it reaches a luminescence center or an activator. So these are dopants or defects purposefully introduced into the scintillator. And then finally is luminescence. So this is just emission of the UV or visible light. So for conversion, there are sort of three different mechanisms depending on the energy of the ionizing radiation. So broadly between 0.1 kiloelectron volts and 100 kiloelectron volts, the mechanism is dominated by the photoelectric effect. So the ionizing radiation will interact with the atom and will ultimately end up ejecting uh, a light to the electron. At higher energies between 100 kiloelectron volts and 1 mega electron volt, it's dominated by Compton scattering. So in this process, the ionizing radiation energy is partially transferred to a valence electron, and some of the energy is then scattered as a lower energy photon. And then interact with the nuclear Coulombic field, and this will generate an electron and its antiparticle positron. So these three processes will generate large numbers of high energy electrons. And we can also look at this process in terms of a band structure for these type of materials. So in this theory, band theory, scintillators are classed as insulators because there's a large energy gap between the conduction and valence bands. And when ionizing radiation is incident onto the scintillator, it will promote an electron from the valence band to above the conduction band, leaving behind a positive hole. The electron will then lose energy as heat through thermalization and reside in the conduction band. Next, energy transfer happens. So these electrons and positive holes will migrate through the material until they reach an activator, which is a defect or a dopant. And these are introduced because they have energy levels that reside between the conduction and valence bands. So once they reach these, they will then drop down and reside into the activator excited state and activator ground state, respectively. And then in the luminescence stage, these charge carriers will recombine, and this will emit a photon through scintillation. And because the energy levels are the difference in the energy levels is small, the wavelength will be in the visible or UV range instead of another ionizing radiation. So another aspect of radioluminescence is Cherenkov radiation. So this is a light that is released when a charged particle travels faster than light in a dielectric medium. So this is a medium that is able to be polarized, and this can be things such as water. So it's a fundamental law of physics that nothing travels faster than light in a vacuum, but when it's in a dielectric medium, it will slow down, and high energy particles are able to travel faster than light is in that medium. And the most famous example of this is the sort of blue glow that is around underwater nuclear reactors. And this is because of Cherenkov radiation. So what causes this phenomenon? Well, when a charged particle moves through a dielectric medium, it's going to polarize nearby atoms into a higher energy state. And when those atoms start to depolarize, they will release that energy as a sort of series of spherical light waves. And when the speed of the particle is less than the speed of those light waves, they will be released and they never touch each other. However, if the speed of the particle is greater than the speed of the light waves, they're generated faster than they can move away from each other. And this will cause them to overlap. And it's this constructive interference of these light waves that generates a cone of visible light behind the particle. And this is the same principle behind a sonic boom. So when a plane travels beyond the speed of sound, the sound waves don't have time to move away from each other, so they are amplified into a large sonic boom. So what are the kind of applications of Cherenkov radiation? So it's used largely in large detectors for particle physics. So there's a large tank of water that was called the Super Kamiokande, and they're now making an even bigger one called the Hyper Kamiokande. So this is used to detect nucleon decays and neutrino interactions as they pass through this large tank of water and Cherenkov radiation is emitted. And there's many, many thousands of PMT detectors which are used to detect that Cherenkov radiation. There's also, you can use Cherenkov radiation for medical imaging. So there's a series of radio tracers that are used for PET and SPECT, and these will emit beta particles. And as they pass through water in the human body, these will release light, and this can be used for medical imaging as well. So we can also use radioluminescent spectroscopy to try and improve the properties of scintillators. And we can do spectral and time resolved measurements. So when we're doing spectral measurements, this will allow us to determine the band gap of the scintillators and also give us information about defects or dopants. It will also allow us to determine the limit of detection. So what is the smallest amount of ionizing radiation that the scintillator is able to reliably detect? Determine the light yield. So that's how efficient the scintillator is at converting ionizing radiation into UV visible light, and also the linearity. So what is the dynamic range of the scintillator as a detector? When we do time resolved measurements, we can determine the responsiveness of the scintillator. So how fast is it? It can also give us information about defects and dopants, how fast charge carriers are moving through the material. And we can also determine the stability. So does the radioluminescence intensity remain constant over time, or does it change? And we can do these measurements using the XS1 radioluminescence chamber. And I'll hand over to Maria to give more information about how we measure radioluminescence practically.
Thank you, Tommy. That was a very interesting introduction to radioluminescence. So now that we know how the mechanism works and we know what it can tell us, I'm going to give an introduction on the experimental techniques that we use to measure it. So what do you need to measure radioluminescence? One second. Yes. You need a source first, a source that provides ionizing radiation to the sample. In this case, we're going to be measuring X-ray photons. So the source hits the sample, and both the source and the sample should be in an X-ray safe enclosure to make the experiment safe. But the photons emitted by the sample in these radioluminescence applications are going to be UV-vis NIR photons, so they can be taken out of the enclosure and into a detection setup, which to obtain the spectral and time resolved information that Tommy mentioned, you need a spectrometer that has both spectral and time resolved capability. It helps to have a photon counting setup just because of sensitivity and also for the time resolution. And it also provides quantitative information. So that's kind of like the general components of a radioluminescence measurement experiment. And as Tommy mentioned, we have a commercial product at Edinburgh Instruments that takes all these design requirements into account, and that's the XS1 radioluminescence sample chamber. So we've developed it with these requirements in mind, and it's an accessory for our photoluminescence spectrometers that can measure steady state and time resolved radioluminescence. It incorporates a continuous and a pulse X-ray source that are inside a radiation-safe enclosure. In the image here, you can see the enclosure here, the XS1 chamber in the front of the image. And there's a light guide, a liquid light guide that takes the visible or UV or NIR light into a spectrometer for analysis. So in the background, you can see Edinburgh Instruments FLS 1000 spectrometer, which would be used in this case for analyzing the signals. So it's an add-on that can be FLS 1000 or the FS5 spectrofluorometer. Here's a schematic of what goes on in this experiment. On the right-hand side, we have the XS1 chamber, and inside it, you can see there's a pulse X-ray source in the schematic, and also a continuous or CW source. In this case, we have the pulse source in the exciting position, so it's exciting a sample, is providing X-rays to a scintillator, and the scintillator emits visible light, which is represented in green here. The light is collected by some optics and then coupled to a liquid light guide. And the liquid light guide takes the signal into the PL spectrometer. So in the PL spectrometer, in this case, the FLS 1000, it has a sample holder for the liquid light guide. And it collects the visible light and it analyzes it. These are double emission monochromator of the spectrometer and a photomultiplier detector. So you can use the same spectrometer for studying standard photoluminescence scintillator if you just use the excitation arm of the PL spectrometer, and then you can switch to studying radioluminescence with the XS1 chamber. So I mentioned we have pulse and CW sources. It's important to note that the pulse source is going to allow time-resolved measurements if your spectrometer is equipped for time-resolved PL. So with something like a time-correlated single photon counting or TCSPC upgrade. If your spectrometer doesn't have this capability, it can be upgraded. I mentioned you can switch between pulsed or continuous excitation. We have the two sources here, and they're just manually swapped into the right position to excite the sample. So on the left, we see the pulse excitation source, and this is triggered by a visible laser, which sits on the side of the chamber. So the laser triggers the source that generates X-ray, that's the sample, and that's the emission light collected. You can see that the light is collected on the other side of the sample. So radiation goes through the sample and we collect the emission on the back of the sample. Here on the right, you can see the CW source, so continuous X-ray source. In this case, it's not optically triggered, so it doesn't need the laser, and it's just easily placed behind the sample. This is what an XS1 looks like in real life, and you can see both excitation sources. So that's the continuous, in this case in excitation position. The sample holder sits there. The pulse X-ray source here, that's the steering chamber for the optics, and the steering chamber for the lasers for excitation. So this is the laser, the HPL 450 is the laser that triggers that pulse X-ray source. And there's an additional laser mount on the left-hand side for direct optical excitation of the sample if your experiments require it. I wanted to talk a little bit more about the continuous source that we use in the XS1. So this is a standard X-ray tube. So in an X-ray tube, we accelerate electrons inside the tube with a voltage drop, and then they hit a target material in an anode, and this target material produces X-rays. The target material of choice is going to determine the output spectrum of the source. The standard that we offer is tungsten, which is very common, but we have others available. And here is the spectrum of tungsten, which it will always show as continuous spectrum with some characteristic lines. And if you vary the voltage that you apply to the source, you modify its output spectrum. So from 5 kilovolts, and as you increase, then you get higher energy X-rays delivered to the sample. So it's very easy to vary the voltage in the sample to modify the energy that you're applying to it. And I also wanted to talk about the pulse X-ray source. That's a little different. In this case, well, the target material is always tungsten. But the interesting thing is the electrons are not generated with a voltage pulse directly. What we do is we have a visible laser, a pulse laser, given very short pulses. We direct these pulses towards the X-ray sources input. There's a window here, and here there's a photocathode. So the photocathode is excited optically with these lasers, and then it's going to produce photoelectrons, pulses of photoelectrons, and these photoelectrons are the ones that excite the target material, and the target produces X-rays. So we go from photons to photoelectrons to, again, X-ray, very short X-ray pulses. These X-ray pulses can be down to 50 picoseconds wide if you use a suitably short pulse laser. This means that we can perform time-resolved radioluminescence if your spectrometer is equipped with a TCSPC upgrade. And if you have a fast detector, you can measure very short radioluminescence or RL decays. I'm going to be using RL throughout the presentation. That means radioluminescence. And the last part I wanted to highlight about the XS1 sample chamber is the range of sample holders that we have available. We have designed it with holders for powders, films, and cuvettes as standard. So this would be the set of standard sample holders. But if you have custom sample requirements, we're happy to design something for you. We have also supplied short pass cuvettes for concentrated samples, or things like an EPR tube holder if you're measuring powders or crystals. I will now move on to introduce applications of radioluminescence detection, specifically in scintillators. And I'm going to use data from recent publications by Edinburgh instrument customers that use the XS1. The first one I wanted to highlight is a relatively simple case, which is using radioluminescence intensity for quality control of scintillators. This is a publication by the group of Sam Stranks at Cambridge University, and they are developing metal halide perovskites as next generation X-ray detectors. They have some advantages like low production costs and wide dynamic range. But a key challenge of these materials is achieving high quality crystals that give you sensitive radiation detection. So this depends on the growth rate of the perovskite crystals. What this group did is they measure they grew perovskite crystals at different rates. So they deliberately produce low quality and high quality crystals. They check their quality by doing gamma ray detection experiments. But at the same time, they also did X-ray radioluminescence using the XS1 sample chamber. And they compared the gamma ray detector performance against the RL intensity. And they found that it correlated pretty well, that high quality crystals gave high RL intensity. So it's potentially a method for screening these materials for scintillator applications very quickly without going into gamma rays. The next example is a more complete publication on the XS1. It's from the same group in collaboration with David Fairen Jimenez, who embedded perovskites into a metal organic framework matrix. Metal organic framework is abbreviated as MOF. The goal of this was to improve stability to moisture, to oxygen, and to radiation. In the paper, they used the term monolith, which describes a bulk form of a MOF rather than a polycrystalline powder. It's better for this application as it's more easily handled. It's more robust as well, less prone to damage by moisture. So they did a set of measurements. The first one is the PL measurements that I wanted to highlight. In this slide, they checked PL stability in moisture and under constant irradiation. So plot A here is showing the change in PL intensity after keeping the sample in a humid environment. And plot B shows the change under irradiation from a laser, that is the photostability. And on the right, you can see what this monolith looks like under white light and under UV irradiation. So the authors concluded that they are stable over hours, weeks, which is a good sign for practical applications. The next set of tests is radioluminescent excitation with the continuous source in the XS1. So that gives more information on scintillator quality and on scintillator stability. First, you can see here the radioluminescence spectrum of just the MOF matrix in the dark color, and then the perovskite material in the MOF in the lighter color. So it shows that adding the perovskite increases the RL intensity and it shifts the spectrum towards visible, which can be useful for radiation detection applications. And the author suggested that the spectrum has contribution from both the perovskite and the MOF. And another important parameter for characterizing scintillator, as Tommy mentioned, is establishing the limit of detection of the scintillator. So this, varying the dose of radiation and measuring the RL intensity, you can establish the linearity and the limit of detection. The performance was similar to commercial available scintillators, but we have the added advantage of the higher stability of the material. And the last graph here is another quite common test with continuous radiation, which is the stability over many cycles of irradiation. The test showed there was a small loss in RL intensity as you irradiate the sample, but very interestingly, the material then returned to normal if you turn it off. So this suggests self-healing, which is obviously a very big advantage for commercial applications of the material as well. And finally, for this publication, they also did time-resolved radioluminescence with the pulse source. So here we have radioluminescence lifetime. So we are applying a short pulse of X-rays here at the start of the decay, and then we're measuring the luminescence as a function of time. And then the average lifetime of the perovskite MOF can be calculated in nanoseconds. This tells us the relaxation process is very fast compared to other scintillators. So here you have two other quite common commercial scintillators, and the perovskite MOF is almost 100 times faster. That means that if you make radiation detectors with these perovskite MOFs, you can measure potentially much faster processes. So in things like biomedical applications, bioimaging, where you're trying to see fast changes, that can have a very good potential advantage. I'll move on to another publication just very quickly. It's a different research group, and they did similar radioluminescence measurements to characterize a scintillator. In this case, they modified copper-1 clusters with halogen ligands to increase efficiency and stability. The type of measurements they made, in this case with a CW X-ray source, are very similar, but I wanted to highlight something that the other paper didn't have, which is temperature-dependent radioluminescence, and it's something that we can equip the XS1 for as well. So they measure RL as a function of temperature using a software control stage, and they compare the standard scintillator without the halogen, that's the gray one, against the halogen cluster scintillator that they were developing here in blue. So they found this area here where RL increases with temperature, that's known as a negative thermal quenching, which they assign to distortion of the cluster lattice by the X-rays. So the negative thermal quenching was more pronounced in the standard scintillator. So it was less pronounced in the halogen cluster, and this suggests that there are fewer traps and potentially higher efficiency of this material. It's just a quick example to highlight how these temperature studies can help you understand the photophysics of the scintillator mechanism. So then you can fine tune the composition to improve its performance. Understanding the underlying physics is going to help you make better materials. The last publication I wanted to highlight goes back to perovskites. They're a very hot topic right now. And it's another published paper, this time from the University of Surrey, using the FLS 1000 and the XS1. So they made perovskite nanocrystal and they embedded them into a PMMA, polymethyl methacrylate matrix. They coated the perovskites with an oleamine surfactant to reduce quenching and aggregation. So the goal of all of this is to make them easier to process and therefore reduce the manufacturing cost of the scintillators. The type of data, again, includes both spectral and time-resolved RL. On the left-hand side, we have the radioluminescent spectrum, which has relatively narrow bandwidth, very similar to the PL spectrum of the material. And again, the green emission band makes it quite suitable for commercial radiation detectors because this wavelength is very easily detected by PNTs or cameras. The RLDK, again, had a relatively short lifetime. The average was 29 nanoseconds, again, much shorter than established commercial scintillators. So such type of very responsive material gives you an advantage when you're doing time-resolved imaging. That concludes a very brief overview of applications I wanted to highlight, and is also the last step of today's presentation. So we've seen how PL and RL can characterize your scintillators and help you optimize their design. I hope I've shown you how a spectrometer that combines both techniques can be beneficial, saving time and cost. Before we finish, I'd just like to highlight our knowledge-based resource in the Edinburgh Instruments website. Here you can access some written resources to learn more about scintillators. So for example, we have an introduction to radioluminescence, if you'd like to go over the basic concepts again, but also some pieces highlighting other customer publications that we didn't discuss today. For example, there's a research highlighter on scintillators for photodynamic therapy with X-rays, or an application note on a liquid scintillator based on energy transfer. I just direct you to visit our website to learn more. This concludes today's presentation. Thank you very much for your attention, and I will be happy to answer any questions you might have.
Brilliant. Thanks, Maria. It was a great presentation. Yeah, we do have a few questions come in already. So we've had one, can the XS1 chamber be coupled the LP980K spectrometer?
Oh, that's interesting. I suppose that this is from someone who has a transient absorption spectrometer. Potentially, yes, for spectral measurements, we could do something. This is not something that we've looked into, but if you're interested, I would advise that you contact us, get in touch with your exact requirements, and then we can look into it for you.
Right. Yeah, we have another question. Is it possible to make measurements at 77 Kelvin using the XS1?
Yes, like I said, this is it's not a standard, but it is an option in the XS1 to put a temperature control stage, and this would be controlled from the software of the spectrometer. So you can do a map of the signal as a function of temperature. And yes, the minimum would be 77. You can also heat up over above room temperature.
Brilliant. Yeah, the questioner has also inquired about price, but yeah, if you get in touch with our sales team, we'll be happy to provide you a quote for any of the products we talk about. So it's another one. What is the shortest radioluminescence lifetime that you're able to measure?
Okay, so that depends mostly on the source and the detector. And I've not gone too much into detail about time resolved luminescence. We have other resources that explain how that works. But assuming if you want short, then you go for TCSPC, and we will use an HPL 450, which is one of our sources, a standard, which is 100 picoseconds, and that's going to define the minimum lifetime you can measure. If you use a fast detector, then you can go down to tens of picosecond lifetimes. That would be the lowest limits. But with a standard detector like a PMT 900 that we have, I would put the limit at like 100 to 100 picoseconds, which is totally fine for most scintillators. If you have requirements for faster, then we can look into a shorter pulse for excitation, but the minimum width of the excitation pulse is going to be 50 picoseconds, which is the width of the X-ray source.
Okay, brilliant. We've actually run out of time for any more questions. If you'd like to ask anything else, you can email us at inquiries@edinst.com. I would also like to point you to another webinar that's upcoming. So next month we'll return with a webinar on automating Raman microscopy analysis with chemometrics. So this will be on March 18th. And make sure you're subscribed to our newsletter or following us on social media, including YouTube, so you don't miss that next one. Finally, thank you everyone for joining us, and we'll see you next time. Thanks.